Hello everyone. I welcome you all for today's lecture series on hydrology and irrigation engineering. The topics covered in the last session was on types of recording rain gauges, that is tipping bucket rain gauge and weighing bucket rain gauge. The topics to be covered in this session will be on mass curve of rainfall, working of siphon rain gauge and radar measurement of rainfall. The learning outcomes of today's lecture session will be able to understand the mass curve of rainfall, and you will be able to study the radar measurement of rainfall. So now let us know what is exactly mean by mass curve of rainfall. From the mass curve, the average intensity of rainfall, that is in terms of centimeter per hour, can be obtained by calculating the slope of the curve at any instant of time. The patterns as well as total depth of rainfall at different instants can be obtained. The recording type of rain gauge is also called integrating rain gauge. The reason is that the curve obtained on the graph is a cumulative curve in respect of rainfall. On y-axis we get accumulated or integrated rainfall, and on x-axis we have equal time increment. This type of curve is in which one ordinate gives the accumulated values is called a mass curve. The total mass curve of rainfall is a plot of the accumulated precipitation against time, plotted in chronological order. It records of a float type and weighing bucket type gauges are of this form. A typical mass curve of rainfall at a station during a storm is shown in this figure. Mass curve of rainfall are very useful in extracting the information on the duration and magnitude of a storm. All intensities at various time intervals in a storm can be obtained by the slope of the curve. For non-recording rain gauges, mass curves are prepared from knowledge of the approximate beginning and end of a storm, and by using the mass curves of adjacent recording rain gauge stations as guide. So till now we have discussed the mass curve. So you can see the graph here. So the graph is plotted against the total rainfall and the time is taken at the x-axis. There are some errors in measurement of rainfall, that is difficulties in the measurement of precipitation. Rain gauge itself may cause eddy currents and may affect the catches of the rain gauge. Evaporation of water collected in the rain gauge, and some rainwater may be lost in wetting the sides of the funnel or the measuring flask. Splash into or out of the funnel may modify the true value of rainfall. So there are instrumental errors, errors in scale reading, dent in receivers, dent in measuring cylinders. About 2.25 mm of water is initially required to wet the surface of gauge. Rain gauges splash from collectors, frictional effects non-vertically of measuring cylinder, that is 10-degree inclination gives 1.5% less precipitation, loss of water by evaporation, leakage in measuring cylinder, and wind speed reduces measured amount of rain in the rain gauge. So, a plotting of mass cumulative value of a variable, it is the function of a time. In this case, plot of accumulated precipitation against time plotted in chronological order will give you the mass curve. The advantage of this rain gauge are that it can record snow, hail and mixture of rain and snow. The disadvantage are the effect of temperature and friction on weighing machines mechanisms may introduce errors. Failure of reverse mechanism results in loss of record. Because of wind action on bucket, erratic traces may be recorded on the chart. These are the advantage and disadvantage of mass curve. Next, let us discuss about siphon or float type rain gauge. This is also called integrating rain gauge as it depicts an integrated graph of rainfall with respect to time. The construction of this rain gauge is shown in this figure. So these are the different components of siphon rain gauge, where it contains the diameter, the funnel diameter of 203 centimeter, which is connected to a ring. Next, it consists of a funnel and a base cover which is made up of a metal and a revolving drum where it rotates in clockwise direction and a chart mounted on it, and a pinpoint arrangement in a clock mechanism, and a float chamber with a float inside in it and a base. So this compartment is again connected with the siphon chamber So due to siphoning action, the water is removed from the float chamber. It consists of a filter in order to avoid the dust and debris accumulated in the siphon pipe. In order to avoid the clogging of the siphon pipe, this filter media is provided at the bottom of the funnel. A receiver and a funnel arrangement drain the rainfall into a container, in which a float mechanism at the bottom is provided. As water accumulates, the float rises. A pen arm attached to the float mechanism continuously records the rainfall on a clock-driven chart and also produces a mass curve of rainfall. When the water level rises above the crest of the siphon, the accumulated water in the container will be drained off by siphonic action. The rain gauge is ready to receive the new rainfall. So this is the working procedure of siphon type of rain gauge. Now let us discuss about radar measurement of rainfall. It is an electromagnetic wave known as pulses are produced by a transmitter and are radiated back a narrow beam antenna. The principle involves radar. The reflections of these waves from the targets or echoes are again intercepted by the same antenna. And receiver detects these echoes, amplifies and transforms them into videos, form an indicator called plan position indicator. The screen of the indicator is illuminated dimly where there is no target or a rainfall, and a bright spot occurs where there is a target and a bright patch. A bright patch here you can see where there is an extended object such as a rain shower. So it indicates whether the rainfall occurs or not by means of a echoes. Radar can produce detailed precipitation information for large areas from a single location in real time. Although radar has been used experimentally for nearly 30 years to measure rainfall, operational implementation has been slow. Today we find that data are underutilized and both confusion and misunderstanding exist about the inherent ability of radar to measure rainfall, about factors that contribute to errors, and about the importance of careful calibration and signal processing. Aerial and point rainfall estimates are often in error by a factor of 2 or more. Error sources reside in measurement of radar, reflectivity factor, evaporation and advection of the precipitation before reaching the ground, and variations in the drop size distribution and vertical air motions. Nevertheless, radar can be of life-saving usefulness by alerting forecasters to the potential for flash flooding. The most most successful technique for improving the radar rainfall estimates have been to calibrate the radar with rain gauges. Simple techniques are combined spare gauge reports, that is 1 gauge per 1000 to 200 kilometer square, with radar produce smaller measurement errors, that is 10 to 30% than either system alone. When high accuracy rainfall measurements are needed, that is average error less than about 30 to 20%, the average of radar is diminished since the number of gauges required for calibration is itself sufficient to provide the desired accuracy. So, for operational forecasting of a river flow and the flash flood or a dense rain gauge observation are desirable, but their installation has not been practical. Thus, there has been considerable interest in utilizing weather radar since it provides spatially and temporally continuous measurement that are immediately available at one location, but scatter and attenuation of microwaves by precipitation targets can be based for estimation of precipitation. Currently, reflectivity data, either alone or in combination with rain gauge, are considered most practical for operational measurement of rainfall over large areas. Distribution that can be obtained by this method, flooding from the storm devastate method. Unfortunately, radar does not measure rainfall rate directly, but rather the backscattered energy from precipitation particles in an elevated volume, and is prone to errors. Variations in the relationship between the backscattered energy and rainfall rate, change in the precipitation before reaching the ground, and anomalous propagation of the beam. This circumvent the errors caused by the variations in the relationship between the backscattered energy and rainfall rate. A number of other possible precipitation measurement techniques have been suggested that utilize various proportions of the radar signals. Since microwave attenuation is related to rainfall rate, it has been proposed that the average rainfall along a path be determined by measuring signal attenuation. These radar values could then be used to determine two parameters of a drop size distribution of assumed shape for which rainfall rate could be turned to be calculated. The potential for radar to improve the warnings of the floods and severe storms, together with the ever increasing availability of inexpensive high speed data processing equipment, stimulated the national service of initiated projects. The backscattered radar power from precipitation particles is proportional to the summation of the sixth power of particle diameter. Drop size distribution has been measured in many types of rains and characteristic. Usually the coefficient increases and the exponent decreases with the increasing convective intensity, even for similar type storms in same geological area. One source of reflectivity measurement error arises from hardware calibration, frequently even after resemble carefully electronic system calibration. Large unexplainable systematic error in rainfall measurement remains. Desirably, that calibration include an independent source, that is comparison with the rain gauge or distrometers. Potential serious sources of measurement errors not associated with the hardware are beam blockage by obstacle close to the radar site, anomalous propagation of the radar beam, the buildup of precipitation films on the radome, and attenuation by precipitation cloud. Attenuation most affects the shorter wavelengths, thus it is frequently advocated that a wavelength of 10 cm to be used for quantitative rainfall measurement. Random errors in signal estimates are associated with the independent mentions of numerous target precipitation particles. The questions for practice is explain mass curve of rainfall, where you need to explain what is mass curve and how it is plotted, and briefly explain the siphon type of rain gauge with a neat schematic representation. Where you have to draw the schematic representation of a rain gauge and mark all the details and explain the working and principle of siphon type of a rain gauge. Next, explain radar measurement of rainfall. So draw the diagram and write how you are going to measure the radar measurement of rainfall. So these are the things which they are going to ask in the examination. So I briefly explained about the radar and how it is measured and what are the errors associated with the radar. So many times in the examination they are going to ask you to draw the schematic representation of a siphon rain gauge, which is very important from the exam point of view. And regarding the radar, write the full explanation that how you are going to measure the rainfall by radar and also the errors associated with the measurement of rainfall by the radar. So in the next session we'll be studying the different what are the factors governing the selection of the site for rain gauge stations and determination of average precipitation over an area. So this is very important from the exam point of view. So determination of average precipitation over the entire area, that I am going to explain you in the next class. So this is all for today. Let us meet with a new session. Thank you very much.